Okay, folks, welcome to lecture 2. We're going to kind of review logs, solving problems and stuff. So it'll be a little bit of review of what we did in semester 1 and in semester 2 as well, with a bit of new stuff too. First of all, though, we're just going to take a quick overview of functions again, just to kind of remind you of the principal parts. In a function, we have an input, kind of gets passed into the function. These are of all different types. And then that produces an output. So we have our input. The nature of the function, is it exponential, is it logarithmic, is it quadratic? And then we have our output. So in science, really important, I emphasized this a lot last semester. Whenever we're carrying out an experiment, we're usually examining a function in one way or another. And in an experiment, what we control is the input and what we measure is the output. Very important to establish those parameters from the start. What's my input? What's my output? That determines how we graph and analyze our results. So just to kind of get into a little bit technical, like what is a function as opposed to an equation, there is differences between them. So an equation is a function if every input only has one output. So they call this the vertical line test. If we pass a vertical line across the curve only cuts the vertical line once. So we can see here, no matter where the vertical line passes, the curve only cuts it once. So each input can only produce one output. It can't produce several. If it produces several, then we're not dealing with a function. And if you can draw a vertical line and it crosses the curve in two places, then it's not a function. So those are the definitions of a function. Now there's a one-to-one function where every input has one unique output. And this is called the horizontal line test. Similarly, we pass a horizontal line over our curve and it only cuts it once if it's a one-to-one function. So again, no matter where the horizontal line is, it only cuts the curve once. Now, in several functions, you can have a many-to-one function. So that's slightly different, where several inputs can produce the same output. And we'll look at a few examples of these in some of the coming slides. So if it's a one-to-one function, then we know it definitely has an inverse. Now, lots of many-to-one functions also have inverses, but if it's a one-to-one, it's definitely got an inverse. So some of the functions we looked at last semester, I'm sure you're familiar with them. And now we're just going to take a look at the graphs of these and determine, are they equations, functions, one-to-one functions. We'll be fairly quick. So here's a circle. We tried a vertical line test, and we can see in several places the curve cuts the vertical line in several places. So a circle is not a function, but it is an equation, x squared plus y squared. In this case, it's x squared plus y squared equals 25. Those questions are moot. Here we have a quadratic. Is it a function? Vertical line test. Yes, it is, because the curve cuts the vertical line only once. Is it a one-to-one function? And we can see it isn't, because there's lots of places there, pretty much everywhere, there's two outputs crossing the vertical line. So this, a quadratic, wouldn't have an inverse. Cubic, is it a function? Yes. Is it a one-to-one? No, because if we could pause that in some places, say here, the horizontal line cuts in three places. So three different inputs produce the same output value of 4. Does it have an inverse? Not necessarily. Trig curve, Is it a function? Ooh, my red limit has disappeared. You get the idea. And we have, is it a one-to-one function? Oh, again, that picture is obviously pulled to the front. But anyway, you get the idea. But again, here there's lots of places. On a trig curve, because this wave goes on forever, you can see the horizontal line can be cut in several places. All that means, guys, is several inputs are producing the same output. And in a trig curve, obviously, this goes on forever. Here's our log curve. Is it a function? Yes. And is it a horizontal function? No. Again, guys, I'm sorry, the line is kind of passing the wrong way, but we get the idea. And finally, exponential function. Again, the line goes the wrong way. That's very frustrating. This one works right. So that's just to give us a quick overview. So does both of these functions are one-to-one? And these are the functions we'll actually be examining in a lot of detail in this semester, and they both have an inverse. When a function is one-to-one, so every function of an exponential, we were looking at exponents last week, that's an exponential function. So the inverse of an exponential function is a logarithmic function. Some definitions of a log there, that x must be greater than 0, a must be greater than 0. Because if a was negative, then every second value would be positive and it would produce an unusual looking graph. And a can't be equal to 1 because a to any power is just going to be 1. We'll look at some of these rules in a little bit more detail. So this is our function written in a formal sense, which is the inverse of this. So this is just a slide from last year. Simplest equation. Y is equal to the log a log bx is the general equation. Here's our typical curve. Remember, guys, the log of any value between 0 and 1 is negative. You cannot have the log of a negative number. And then the output grows slowly as the input grows quickly. So it's not continuous because it doesn't exist on the left-hand side, on the negative side. Output grows slowly. And some examples, dog age, memory retention. We look at these examples towards the end of the lecture. And then we have our log scales that we looked at last semester in quite a bit of detail. So now we're just moving into maths. That's just to kind of establish where we are. We're looking at functions. We'll be looking at their inverses. So that's just was just to give a quick preamble to that. So really last semester, or in first year, we learned two main skills. Using log and 10 to the power of x to solve equations, or ln and e to the power of x if we were looking at a natural function, a natural log function. And then we were using the laws of logs to compress an expression involving several log terms into an expression with only a single log term. So we're going to have a quick review of these now. And that's really what most of the lecture is about. So converting exponents into logs. So here we have our here we have our exponent. Now here's the base, guys. So straight away I know if I want to manipulate this equation, I'm going to have to remove that base. How I'm going to remove that base is by using a log with the same base and apply it to both sides. So the log of 3 is equal to the log of 3 of 81. These cancel out because they're inverse functions. We get 4 is the log to the base 3 of 81. And finally, you write your log on the left. And that's us there. Here, guys, I'm going to speed it up a little bit. I need to kill my base of 5, so I'm going to get log to the base 5 of both sides. So on the left, we'll have log to the base 5 of 625. When I get the log of this to the base 5, guys, the log to the base 5 and the base of 5 cancel each other out. And we just get that. So that's our answer. So it's perfectly fine, guys, certainly in semester 4, just to speed through them. You don't need to show this intermediate step here. Another example. Get log to the base 10. So 10 is my base. I want to kill the exponent, so I want to remove his base. So when, first of all, I'm getting log. So it's just log. Log on its own, guys, always means it is to the base 10. So when I apply log to the left hand side, that kills the base. And now when I get the log of the right hand side, finally then write my log on the left. So the log of 0.1 is minus 1. This is an essential skill, guys, so you just got to get used to this idea, because the first 3-4 weeks of this semester we're just going to be dealing with logs and exponents. Here, guys, I need to kill e, so I'm going to get log to the base e of both sides, which we're more familiar with as ln. When I get the ln, the natural log of the left hand side, that kills my base, so I'm just left with 2. And that's my answer then. The natural log of 7.389 is 2. So, now in these ones, guys, just see if you can have a go first. So that's what that little symbol was. I forgot, my sequencing isn't great, but sure, we'll work through it. So pause the video here and see if you can have a go first. So on most of the slides now, guys, it would make sense. Normally in the lectures, I would have these up on the screen and I'd give you guys a minute or two to have a go. So it'd be best to kind of replicate that with these videos. Just pause the video and have a wee go. So here, guys, now these tend to just kind of confuse people a little bit more, so I'll work through them, the first 1 or 2 in a bit more detail, and then I'll speed it up. I want to kill log to the base 3. I want to kill him. How I do that is, oh, sorry, not E. I raise both sides as a power on 3. So now this looks a bit weird. So what happens is both sides are raised to the power of 3. And now these cancel each other out. So we've removed the base. So we get 9 is 3 squared. And that's us then. So I think everyone's familiar with that. Similarly here, guys, I need to kill my log to the base 2. So I'm going to raise both sides as a power on 2. And again, it becomes 2. So I'll do the easy side on the right first. And again, these kill each other off because we've designed that to happen. And that's our, finally just write our exponent on the left. So again, guys, certainly in this semester, there's no need to write these intermediate steps. Normally, you just go straight towards your solution. So now, guys, I'm going to speed this up. I'm going to raise both sides as a power on 10 because that's the base of the log. When I do that to the left, it just kills the base, kills the log, sorry. And there we are with our answer. Here, I need to kill log to the base e, raise both sides as a power on e. So we do it to the left. When we do it to the right, guys, that kills him. And there's our answer popping out. So on your journal, there's a few questions that examine that skill. Now we're going to look at solving log equations. So same idea. I want to get x on its own. I want to kill 10 to the power of. So I'm going to get log to the base 10 of both sides, just the log really. When I do it to the left, I get x. And when I do it to the right, 0.691. Get your calculator. The log of 0.691. Now, remember, this is a number less than 1. We're getting the log of it. So first thing, my answer is going to be negative. Remember the graph. The log of any value between 0 and 1 is negative. And we get minus 0.16052 dot 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 dot. Usually, guys, certainly 3 decimal places will be loads. So we could, minus 0.161, whichever you prefer. If we were asked to say 3 significant figures or 3 decimal places. Here's another one with an extra step. Now we can't kill the log first, guys, because of this plus 1. Remember, we want to isolate x. We must remove what's furthest away from him first. So a first step, guys, is we're going to subtract 1 from both sides. We want to get rid of this guy first. So now we'll get the log of x. When I subtract 1 from the right hand side, I'll get 1.6205. Now I'm going to kill my log. It is log to the base 10. So I raise both sides as a power on 10. When I do that to the left, that kills the log. And again, get your trusty old calculator. 10 to the power of and we get 41.73. And if we want to go to one more decimal place, we'll throw in a 5 there. Now again, guys, pause the video, have a wee go yourself, see how you go, because otherwise, guys, if you're not really practicing and seeing where you're making the mistakes, the learning curve is going to be a lot slower. So please pause, try this one out, and then try the next one, and we'll see how we go. So now I need to kill ln. Remember, log is to the base e. So x is here, guys, but what's furthest away is this. So that has to be the first to go. So I'm going to raise both sides as a power on e. When I do that, kills the natural log on the left. Now I'm going to subtract 1 from both sides. It's always best, guys, not to hit the calculator until the very last step. So now I can get my calculator, shift, natural log, that brings up my e. And we get 13. Oh, sorry, that should be minus 1. Always check. So that's actually, 11.182. Looking at the problem D. Okay, there's several things acting on my x, and again, guys, in a way, this is formula manipulation, but I need to get rid of the furthest away thing first, which is the 2. So I divide both sides by 2. E to the power of x plus 1 is 50. Now I need to kill my e, so I get the natural log of both sides. Remember, that's log to the base e. When I do that to the left, when I get the natural log of the left-hand side, we just get x plus 1, get the natural log of the right-hand side, and finally then x is equal to the natural log of 50, and we're going to subtract 1 from both sides. Let's write a little. So finally we get our calculator. Natural log of 50, close the brackets, be careful there, minus 1. And it's 2.912. And again, yeah, my pause symbols, my animations aren't great. I'll work on them. Here's another 2 guys again. So have a go. So there's the little pause symbol. And take your time. I'm just trying to kind of move a bit quickly because I'm conscious that you lot have a limited attention span. So I'm trying to get through them as efficiently as possible. So here, guys, again, this is really, we're getting into the nuts and bolts now of kind of second year maths. You know, things are a bit more challenging. There's several things acting on the x. The closest thing is the 3. He's the last to go. Then the minus 2. Anything inside the bracket indicates it's closest. So the furthest thing away, guys, is the 2. Then the log. Then the minus 2. And then the 3. That's your order of removal. And that's the most important thing, guys, is getting that right. So 2 is joined on by multiplication. We divide both sides by 2. And we get the log of the brackets is equal to 0.53. Now we want to kill the log. It's log to the base 10, so we raise both sides as a power on 10. I remove the brackets. Now again, guys, don't be tempted to dive for the calculator here. Leave it as it is. Because if you get the calculator now, you're going to be dividing your answer again. So you're going to be rounding up when you get the calculator, and then you're going to be dividing by 3 in a couple of lines. And so you're going to be rounding up twice, which compounds your error, or compounds the lack of accuracy, I suppose, is the best way to put it. So now we want to move the 2 away from x, so we add 2 to both sides. So 3x is equal to 10 to the power is 0.53 plus 2. And finally, we want to get rid of the 3, so we divide both sides by 3. 10 to the power is 0.53 plus 2. Notice everything on the right, guys, gets divided by 3. So now we get the calculator. You can use the fraction function on your calculator if you want. So we have 10 to the power 0.53. Drop the cursor, plus 2. And always check, guys, make sure that what you're writing in looks similar to what you've written on the page is similar to what you have on your calculator. So this gives us 1.796. Part F. Okay, first step, we're going to get rid of him, divide by that, then we're going to get rid of the natural log, then we're going to get rid of the 7, then we're going to get rid of the minus, and then we're going to get rid of the 3. So it actually it's literally a linear, we're working our way from left to right. I'll just remove them. So divide both sides by 0.25. I'll just write it in. So we're going to have the natural log of the brackets. And now 1.75. It's going to give me an even number, thinking about it. It's going to give me 7, I'm pretty sure, but I will just double check. Yep. Now we want to get rid of the natural log, raise both sides as a power on e. That kills the natural log on the left. Again, don't reach for the calculator just yet. We're going to subtract 7 from both sides to move this guy. So we'll have minus 3x is equal to e to the power of 7 minus 7. Now you could move the minus if you wanted, guys, but I'm just going to do it all in one go. I'm going to divide both sides by minus 3. So x is equal to e to the power of 7 minus 7 all divided by minus 3. And because I'm just looking for an answer, guys, I don't really care about the minus 3 being on the bottom or anything like that. Get my fraction function. E to the power of 7 minus 7 and all divided by minus 3. And we get minus, which we'd expect because of the minus 3 on the bottom, 363.2. So this is a very important skill, guys, and in the journal then I have a bunch of questions which are going to test you on these, and we'll push things a little bit further as well in the next lecture once we start looking at the log rules, and then we bring this skill to play as well. Very important now, guys, manipulating log functions. So it's pretty much exactly what we've been doing, but we just don't have numbers to play with. So we want to rearrange the function so that t is the subject. So what I want to do is simply leave t on its own, and it's the exact same process, guys, as I did before, except we just don't get to play with a calculator. First step, I want to get rid of the natural log, and then I want to get rid of the minus 1. So to get rid of the natural log, I raise both sides as a power on e. So we're going to get e to the power of r is equal to t minus 1. Now I want to get rid of the minus 1, so I add 1 to both sides, and I get e to the power of r plus 1 is equal to t. And finally, remember to write your subject on the left. And that's our answer. No calculator required. Rearrange this function, so r is the subject. So exact same process again. Actually, I'm working, r is on the far right, so I'm literally working from left to right. I need to remove the 10, then the log to the base 10, then the 2, and then the minus 0.2. So first step, divide both sides by 10 to get rid of him. T over 10 is equal to the log of the bracket. Now I want to get rid of the log. So it's log to the base 10. We raise both sides as a power on 10. So now we've got 10 to the power of t over 10. So don't be put off, guys. Just because it looks weird, like you're doing science maths, there's going to be a lot of weird looking stuff going on. Now I want to get rid of this 2, it's joined on by a plus, so I'm going to subtract 2 from both sides. So 10 to the power of t over 10 minus 2 is equal to minus 0.2r. And finally then, guys, I want to remove him. Like I said, you could just remove the minus first. But I'm going to get rid of the whole lot. All of that's joined on by multiplication, so I'm going to divide both sides by minus 0.2. So we're going to end up with 10 to the power of t over 10 minus 2 divided by minus 0.2 is equal to r. And finally then, guys, write my subject on the left. Now I'm going to run a minus across the top, change all the signs. So that's going to give me 2 minus 10 to the power of t over 10. I've changed the signs on the top, and I can change the sign on the bottom. And this then just looks a lot better, guys, because there's the minimum amount of negative signs. Now we have this one, rearrange this function so that p is the subject. Looks tricky, but same process, guys. Kill the natural log first. We want to open out the bracket so we can move the 2p. Cannot move the 2p at the moment, guys, because it's shielded by the natural log. E to the power of h. This now kills the natural log on the right over 2p. Anytime your subject is on the bottom, or anytime you have a rational term, a fractiony looking thing, always get rid of whatever's on the bottom. Put brackets around it and multiply. So multiply both sides by 2p, and we get 2p e to the power of h is 3t plus 1. Now I'm going to rewrite this, guys, as simply just p by 2e to the power of h is 3t plus 1. And now I've just rearranged because now I can get rid of everything inside the brackets by division. So p, I'm going to divide both sides by 2e to the h, and we get p is equal to 3t plus 1, all divided by 2 e to the power of h. And then I'll usually be given values for t and h, and I can calculate p. But this manipulation skill, guys, again, is very important for this semester. So I hope that makes sense, guys. We're just going to take a look at a couple of practical scenarios. These are developed in your logs, or in your journal, sorry, so you're going to kind of need this skill to answer the questions in the journal. So one of the practical applications, this was, I'm big into dogs myself, so I found this research fascinating. So just last year, guys, or 2 years ago, they've kind of found this new way of aging dogs. Now the study was based on Labradors, but they think it applies across most dog breeds. So a lot of people say, oh, a dog year is equal to 7 human years. It's not like that at all. Dogs, their methylation rates, that's kind of the way the cells age. You guys will probably know a lot more about that than me. But this is the function now. It's actually a log function. This is kind of a recent study. I have the link in the very bottom of this page. So you can see it's a log function. So for a 3-year-old dog, at the moment we're just going to take a look at a couple of examples. We're going to feed 3 in here for the dog's age. And when you get your calculator, 16 times the log of 3 plus 31. So a 3-year-old dog is nearly the equivalent of a 50-year-old human. Similarly, for a 6-month-old dog, it's nearly 20 years old. Now, on your journal question, I start asking you, like, kind of, well, if you wanted a dog to be 100 in human years, how old would it be in dog years? So you actually have to manipulate your formula for dog's age. And this is the study then. Now, this is just where I found a study, but Yeah, it's quite interesting, especially if you're into dogs. So essentially, guys, dogs age like you can see here in the first 2 years of their life, they kind of hit nearly 44. They're nearly a 44-year-old adult. A 2-year-old dog is kind of the equivalent of nearly a 44-year-old adult. And this is our typical log curve. And one of the neighborhood dogs just passes by my window as I say that, peeing in my garden. But anyway, what can you do? There he goes again. Now, so again, guys, there's going to be a question examining your skills on manipulation to do with this equation, the dog's age equation. And memory function is also kind of a log function, but it's a negative log function, as we'll take a look. So this is again another study. So students taking part in a psychology experiment attended several lectures on a subject and they were given an exam. Every month for a year after the test, the students were retested to see how much of the material they remembered. And the average scores for the group, so they kind of averaged out the scores. And you can see again, it's a log function. Now this minus sign changes the shape of the curve, so it's going to be different to the dog curve we saw earlier because of that minus sign. And they only did it kind of this function only holds for the first 12 months. I think that was actually the length of the study. Obviously, a bunch of students are going to get tired taking the same exam every month for a month. So I'd imagine there's a limit to the amount of participation you can get, willing participation. So this is our function here. This is what it looks like, and it's actually quite similar to the dog one, only it's flipped upside down. So what was the average score in the original exam? We simply feed 0. T was equal to 0. That was when the test was first taken. So 75 was the average score. What was the score at the end of 2 months? Again, just feed in the average score, 2. And the average score then was 68. And obviously, people's memory are going to fade over time. The question on your journal is going to ask kind of how long would it take for the average score to drop to, say, 60 or 55 or something like that. So we need to manipulate the function. Now, instead of FT, guys, you could just write S for score. And then start manipulating. Move over the 75, move over the -6, get rid of the log, get rid of the +1, and then you will have isolated T. If I was asking you how long would it take to get to a particular score, say how long would it take to get to say 55, then you could put 55 instead of S for score, and away you go then. So that, guys, finishes us up on this lecture. I hope it kind of wasn't too quick, but again, with all of my videos, guys, please kind of pause and practice the work before I complete the problem, and you really will get the best value out of this module. And I know it mightn't seem it, guys, but it's the quickest way to work through the material. Is every time you see a problem appear on the screen, pause the video, give it a go on a bit of rough work, and just see then if you're making any mistakes, and if the mistakes are kind of repetitive, then you just need to adjust your technique a little bit. So thanks again for watching, guys. I'll finish up here and we'll chat to you again shortly.